Hey, my name's Yusuf, and today I'll be going over Lab 3, Black Holes. Introduction. The purpose of this lab is to analyze gravitational forces acting on objects in space and make conclusions based on physics principles. The first part of the lab explores the motion of a star orbiting a black hole to estimate the black hole's mass. The second part involves calculating the initial velocity needed for a spaceship to safely travel around a black hole. The lab relies on Newton's law of universal gravitation, shown down here, to determine the gravitational forces between the star, planet, black hole, and spaceship. The momentum principle is also heavily used to predict how these forces will affect the motion of the star and spaceship. Here's a preview of the main results. I found the mass to be 8.8 times 10 to the power 33 kilograms for the black hole, and I found the lowest safe velocity that needs to be achieved by the spaceship to escape the black hole to be 600,000 meters per second. So part one, finding the black hole's mass. The system is the star, the surroundings are the black hole. And here's our code. So we start off by declaring a seed that randomizes certain variables. Over here, this is how we initialize the graph and the axes and all the colors. And down here is where all of our variables get initialized. We have the gravitational constant, the mass of the star, which is 2 times 10 to the power 30 kilograms, the time intervals between imported data points, which is 1 day, 24 hours, 60 minutes, 60 seconds. And over here is our velocities that were calculated based off of the random numbers generated from the seed earlier. Down here, we declare the initial velocity, the final velocity. We get the momentum by multiplying mass times velocity. And we find the change in velocity, change in momentum. We find delta p over delta t by dividing the two. And because of the momentum principle, we know that F net is equal to delta p over delta t. Then we want to calculate the unit vector of the change in momentum in the parallel direction. So to do that, we simply take the vector itself and divide it by the magnitude. We then find the magnitude of that value by getting the magnitude of the final momentum minus the magnitude of the initial momentum divided by the time. And then we find the actual vector by multiplying that magnitude by the unit vector. And as per the momentum principle, we know that F net is equal to delta p over delta t. To find the perpendicular one, we can simply subtract the F net minus the parallel component, and then that gets us the perpendicular component. And once again, we know that because of the momentum principle, these two are equal. And down here, this is how we calculated the mass of the black hole. So here is the calculations, how we did that. We know that F net in the perpendicular direction is simply equal to the force of gravitation. So once we rearrange, we can find M. And that equation is simply represented over here. And down here is how we update out all of our positions and draw everything. So when you run this program, we get a bunch of data points that occur as we complete the orbit. And our results were a bunch of data points. Not all of them are shown here, but once we average all of them, we got this 8.8 times 10 to the power 33. And now moving on to part two, ship launch velocity calculations. The system is a ship, and the surroundings would be the planet that is taking off within the black hole that's nearby. And here's the code for that. So what we do first is initialize the graph and all of the colors and axes. And these are the initial conditions, the mass. This is the mass that we found in our part one. These are the mass of the planet, the ship, the delta t, the gravitational constant, and this is equal to 4 hours of running simulation. So four times 60 minutes times 60 seconds. Planet speed is calculated over here. Its velocity is here. I can bring that into a vector. And this is the lowest speed that I managed to get that would allow for the thing to take off without crashing or becoming absorbed by the black hole. As you can see, there's no x component involved, so we simply had to take off in the y direction. And over here, this is essentially how we calculate all the net forces. So we simply found uh, the vector we simply found the distance between the two. Then we found the unit vector, and then off of those, we were able to calculate the actual one using Newton's gravitational law because we had the direction and the magnitude. That applies for this, and to get the net forces, we simply added them up. Then updated the velocity and position based off of the position update formula and velocity update formula, and then we let everything run. As you can see, at 600,000 meters per second, it's able to escape everything. Here's just a reiteration of that result after the discussion. Numerical inaccuracies may arise, particularly in the calculation of black hole's mass, if the time steps between data points are too large. This could lead to less precise force and mass estimates. In the spaceship velocity portion, the initial velocity was estimated through trial and error, with 600,000 meters per second working for the simulation. However, the actual required velocity is likely more specific, probably as a decimal, and should be determined with greater precision. Additionally, limited observation time in the second part of the lab could lead to incomplete analysis. For example, we only did 4 hours. Without a longer time window, it's possible to miss critical events like spaceship crashing or being pulled back into the black hole after the initial simulation period. Conclusion questions. So the net force on the star represents the total gravitational pull from the black hole. The rate of change in momentum describes how the star's velocity changes over time due to this gravitational force. The parallel component of the momentum affects the speed, while the perpendicular component impacts the direction. The orbit is not perfectly circular here, so there is a parallel component, meaning the speed was changing throughout the process. So, to get the spaceship to enter an orbit, I actually had to add more of an X component. If you may remember, earlier it was at 0. So by adding the X component, it was able to get closer to that and sort of wrap around to get that orbital motion. I also had to decrease this to make sure that it doesn't fly off. Thank you.